dynamic model types. We need some way to categorize models used for dynamic systems. One way to do this is to leverage our knowledge of programming language taxonomy and use similar categories that we use there: declarative, functional, and constraint. An example of a declarative language is Prolog, and Lisp is a good example of a functional programming language. Most imperative languages that we are familiar with today are procedural in nature, and we can consider procedural language to be subsets of functional languages. A procedure is a type of function that does not have a result, or that does not produce a result. So procedural and functional can be considered to be identical if we allow procedures to calculate results that are useful elsewhere. The family of constraint logic programming languages and applied mathematical languages such as Maple and Mathematica are examples of the constraint approach to modeling. Let's consider that you are out walking in the neighborhood where you live and someone, call her Laura, in a car asks for directions to a well-known landmark, say the football stadium. Your job is to provide a model, a dynamic model, that captures the dynamics of the car and driver and achieves the goal of Laura getting to the stadium. We're going to take this example and run through three types of models: declarative, functional, and constraint, to illustrate the differences, to compare and contrast the three model types. So let's look at the first type, which is declarative. How would we employ a declarative model in trying to get Laura to the football stadium? In this case, you would take out a map and show intermediate places, successive in time, where Laura needs to be in order to get to the stadium. In lieu of a map, you might instead point out intermediate landmarks from a neighborhood, from your neighborhood to the stadium. And in doing so, you would be demonstrating a declarative modeling approach to process specification. The second approach is functional, which again encompasses the idea of procedure. You tell Laura how to get to the stadium using commands. You say, turn right out of the neighborhood onto 16th Avenue, right on 34th Street, and again right on University Avenue. And you continue in this fashion to define a cookbook approach to getting Laura to the stadium. The third approach in telling the driver Laura how to get to the stadium is constraint, which means that someone specifies rules or constraints. By following these rules, dynamics are achieved. So what you do is you tell Laura to get to the stadium by first navigating, using some other approach, to the neighborhood entrance, and then hug the right side of the road, and then you say stop when you reach the stadium. Now, as a summary of these three types in this story, the declarative approach is likely to be the most intuitive of the bunch, while the functional reminds us of assembly lines and cookbook procedures. Now, even though this constraint approach may seem primitive and a little odd for this particular driving exercise, nature tends to operate in this fashion, and so that's why constraint models turn out to be very useful. Let's start out then looking at declarative modeling by overviewing it. The components of a declarative model includes states and events and their aggregates. If we aggregate states or events together, we create abstract container-like groups. For instance, we might cluster together a group of x, y coordinates on the plane to form living room. The state of a person, labeled position, can be a coordinate x, y, or the name of the room that the person is standing in, such as the living room. So the name of the room is really a higher level, more abstract state. If we connect states and events together with connectors or transitions, we can create a complete declarative model. With functional modeling, the components of a functional model include functions and variables. As in the declarative case, we can cluster functions and variables together to create more abstract and complex models. You know that your refrigerator has many functions, but if you were to take any one of these individual functions, such as the function of making ice, you surely could subdefine this function into even a greater number of smaller functions, and so on and so forth, until you get down to the lowest level of mechanics or electronics that is used by the refrigerator in order to make ice. Variables and functions can be connected together to create complete functional models. Equations are a good example of constraint models, as are logic programming predicates. Predicates can be satisfied, and equations can be solved by using a variety of common rules for manipulating these expressions. When the solution results in a time-sequenced set of states or events, then the equations are said to be dynamic models. One steers an equation by telling the process where to start, which would be the initial conditions of the equation, what to do when an edge or a boundary is reached, these would be the boundary conditions, and when to terminate. We've described an overall approach for modeling and simulation that uses model structures whose categories mirror that of programming languages: declarative, functional, and constraint. In this way, modeling for dynamical systems and programs can be viewed in the same light. Programs are types of dynamic systems as well. Declarative and functional models tend to work best for defining the dynamics of artificial systems containing cognitively oriented state and event spaces. And constraint models, on the other hand, are widely used for representing laws dictating how nature operates.